speaker for you today. Tim Hunter is actually a former Databricks employee, and he'll be introducing DDS, a data-driven framework, a software framework in Python that makes collaborative programming with data fast, easy, and reliable. So just a quick reminder, this is part of the Data Plus AI online meetup group. There's a link there to join. I'll drop that in the YouTube and LinkedIn chat spaces. It's a great way to stay up to date in all the content that we're going to be delivering. We have a lot of awesome talks that we're planning for the new year. So we'd love to have you join us. So if you join the meetup group, you'll get notifications in your email of all the upcoming sessions. And then if you'd like to check us out on YouTube Live or LinkedIn Live, we always stream to those spaces and have the chats open as well. So we'll be monitoring those. So lots of different ways to join, however you'd like to. And also too, if you do RSVP through meetup.com through the meetup, you'll join us through the Zoom, and then there's also the Q&A panel too, which allows you to ask questions. With that, there's one thing that I'd actually like to share with you all. I shared it a few times, so we're really excited. So I wanted to plug it one last time for the end of the year. We have a new vidcast series that some folks from our team have started. It's called DataBrew, and it's with Denny Lee and Brooke Wenig. And they explore various topics in the data and AI community. They interview a variety of subject matter experts in data engineering and data science. So I highly encourage you to check that out. I'll post that link in all the chat spaces as well, so you can check it out. And it's available on Spotify, which is really awesome, and also on Apple Podcasts. So I hope you'll check it out and let us know what you think. So with that, I'd like to pass it off to my co-host and my fellow teammate, who's also going to be helping answer questions and moderate those chat spaces. Jules, take it away.
Well, thank you very much, Karen, for that lovely introduction, and welcome to all of you, wherever you are, whatever time zone you are in. We're really delighted for us to join the last one. Today, it's really my honor and my pleasure to introduce an old friend, an old colleague from Databricks, who is not well known in the big data space. He's no stranger to it. For the last 6 years, he has been working in the big data space for a while. Since his early days, when he was doing his PhD at MPlab in Berkeley, he was working on Spark before Spark became a project. And then after that, he joined Databricks. And during his tenure at Databricks, he contributed quite a bit to the Apache Spark project, particularly the MLlib. And he also brought us popular packages that he co-created, such as graph frames, which were equivalent to the RDD-based graphics. Those of you who are familiar with Apache Spark. You also co-created most recently a very popular project called Koalas, which is really a way for you to do distributed EDA on Apache Spark. Instead of using pandas, you can actually use Koalas. And he also brought us graph frames and tensor frames and Databricks pipeline, deep learning pipeline that allow you to do distributed computing on your cluster. And then more recently, after he departed, he went to Amsterdam and is heading the AI efforts to do at the bank called ABN AMRO Bank. And today he's going to share with us, what does it actually mean to do data-centric programming? As we know, we have sort of entered the zeitgeist of big data, and data is centric today. We're moving away from doing a lot of code-centric programming to data-driven programming. And so what does it actually mean to build pipelines which are catered around data-driven? So he's going to tell us about what is that and what does it actually mean and how you actually do that for the data scientists. So without any further ado, Tim, please share with us, what does it actually mean to do data-driven programming in the Spark 2.0 framework, or at least Software's 2.0 framework. Thank you.
Also compatible with Spark. Thanks a lot, Jules. Thanks a lot for the introduction. I'm very pleased to be able to join back all my former Databricks colleagues here for this meetup. So let me see if the screen is properly shared before moving on. Okay, so I am sharing my screen. Is it all good, Karen?
Yes.
Okay, perfect. So yes, I'm very excited to be able to come here and talk to you, I think, I hope in a fairly informal manner about how we can envision the integration of data with our regular data science programming. And that's what a lot of people call now software 2.0. So we have quite a few things that I would like to share here. First, I want to review with you some of the scene that we're used to about the challenges of integrating machine learning, data, and traditional code software, and software. And I would like after that to introduce a new software package for Python that I have created and that has been developed within the bank in Europe here, and that I believe really helps in integrating the machine learning data and all the workflows and pipelines that go around that. And I will show you what it looks like on a small Databricks example. So quickly to set up the scene, if we look like the typical functional aspect of a team that has to do data science, typically this team is in charge of maintaining a few data pipelines. And what does it look like in practice? They get some raw data, some data that they do not control. Then they need to solve a certain business problem, so they will detect typically some issues with the data they have, acquire and gather some new label data that will help in addressing these problems. And these problems could be data quality, it could be a model misperforming, misclassifying some objects, and so on. So using this newly acquired data, new models can be trained, deployed, and then these models then will eventually lead to some new raw data, which will lead to another cycle in this loop here. This is the standard paradigm that you find in other projects such as MLflow, SageMaker. This is how most functional teams in data science operate when they want to use machine learning. So now when we look at this cycle, we have multiple ways, we have multiple perspectives on that. One that I would like to point out, even though it seems fairly natural and fairly obvious, is that all of these aspects, going from raw data to deploying models, training these models, require computer code. Essentially, everything that we do in data science will require these days computer code. And this computer code can be written by using IDEs, using notebooks, but it's always at the end of the day a computer code. Another aspect that is also crucial in these systems is that these teams do not operate independently, and the output of one of these teams, being it a model, being it some new process data, will be the raw data of another team, will be the input for another team. And even beyond simply a small cascade, this tends to actually mesh and integrate in a very complex fashion. And this leads to a lot of coordination overhead. So why that? So to recap, teams usually operate within their own units, and cascading changes in the data or in the models or in all the artifacts do not propagate easily, given the typical structure that we have for doing that. And in order to do that, most of the frameworks or most of the processes introduce a large overhead to coordinate these cascading changes. So this leads to drop in productivity, lower confidence in the results. How often do we simply click on the button to say, let's rerun everything just to be sure that we have the latest version? Or we have some other ways to post it to Excel spreadsheet with the latest version, simply because we're not sure about how to rerun it. So when we look at how so far these issues have been addressed, they tend to be fairly specialized on two aspects. One aspect is some solutions such as, for example, MLflow focuses on one fragment on the pipeline, which is the data ingestion. If we consider, for example, data pipelines, or If we look at MLflow, it focuses on the machine learning aspect. That's so this is just a fragment of the whole cycle that I was discussing about. Another traditional focus is around one specific technology. For example, around SQL, there are a number of tools like dbt for being able to chain and assemble all these data frames together, for example, or around Spark, for example. So this is why at the bank we thought about this concept of data-driven software, which is about trying to address both of these limitations by helping users where they are and what they have right now, and with the problem they have right now, and with the code that they have right now. And by doing that, we're trying to solve the problem of reproducibility and integration between different data stacks by keeping the interface simple, by abstracting away from the users all the questions about reading and writing objects, data frames, and so on, and by unifying all the products of data pipelines, being it data sets, model, statistics, under a single namespace, so that there is no confusion about what system is being used in practice underneath. And this abstracts the storage layer. So this is the approach I would like to introduce to you. So to talk a bit about the design of it, users of data-driven software, DDS, can track any sort of objects in the Python programming language. So this could be Spark or Pandas data frame. It could be machine learning models, also even remote objects stored on S3. This is just anything that can be tracked inside Python. There is no need for registering a schema. There is no need for defining a schema. This is strictly taking what users have and with a few annotations, being able to track where this object should go. And as I mentioned, the integration with Python is particularly important, and the focus on Python is one of the crucial design considerations, because most of the users these days who want to do data science tend to write their code in Python with some other libraries, but Python written in different languages. But Python tends to be the glue language that binds everything together. And finally, and you will see, I think I'll give more examples in the next few slides. One of the consideration is to track all the objects that are being created by the users, and just focus on tracking this. So if you launch a website, if you launch a web server, this is not going to be one of the aspects. All it does is tracking any sort of data artifact that you create out of it. So how does this translate in practice? So here I'm going to talk about, I'm going to repeatedly talk about data functions. And you can think of data function as being a Python function that returns a piece of data that is of interest. It could be a machine learning model, it could be a Spark data frame, anything that you would like to track and that tends to be used by other tools or by other teams. So every data function is associated to some output path, and it could be anything. It could be called my model, something else. We'll see a couple of examples, as long as it looks like a path in some file system. And this is the crucial difference compared to some other systems, because so far it looks pretty generic. Every data function can also be reduced to a single signature. And you can think of the signature as taking the function, all its dependencies, all the sub-function that it calls, all the variable it depends on, putting everything into a single Python file and computing a hash of it. And if we assume that these data functions are deterministic, this means that if your code is the same, the signature is going to be the same, and that means the data that you want to output in this data path is going also to be the same. So to take a small example, here is a small data function which for example would produce some training data, and I'm just going to annotate it with using a Python annotation to say that I would like the output to be some object in a file system called the training data. This is going to be what I want to refer to it. And to it, I can associate two things. One is a unique signature computed by taking all the code here, all the dependencies, and I can calculate a unique unique signature for that. And the other piece that I associate to it is this path, which refers to this function. And because this function right now has this particular signature, I can associate this signature to this path. So how does it help us in practice? So if we look at as a small example where, for example, we would like to calculate a model based on bigrams or n-grams, actually, any sort of n-grams here. This is what the standard pipeline would look like. We load some text, we extract all the n-grams from the text, and then we train a model based on this on these n-grams. That after parsing, we can have a learning rate, we can have a lot of parameters. Then, of course, we want to see how good our model is, so we need to compute some accuracy. And in a standard way, we would print this score so that we would see what it looks like. And because we want to keep this model, use it in some other pieces of our pipeline, we are going to use some standard Python tools like the pickle module to write it onto our storage system, onto our local file system. Now, what would it look like with DDS? So let's say that we want to keep the model and that we want to keep all the statistics and the scores. So we can annotate our function calls here to say, when we run the model with all these arguments, we would like to keep the results in our file system associated to the name model, and also, of course, use it afterwards. So this is why we still have this variable. And then when we use, and we're going to do the same thing for the model statistics. We're going to compute the accuracy of our model, and we want to keep the score along with the model in our file system. So this way, no need to try to print it. We have a standard place where everything is going to be associated, and no need to think about how to write it. The framework is going to keep an account of how to write the systems, how to write this, and how to read it afterwards. So how does it help us afterwards? Because so far it looks like a lot of syntactic overhead. Let's see what it can do for us. So let's say we start with our small program here, where we want to compute bigrams, and if we decide afterwards that we want some trigrams, that's a reasonable assumption. And let's say that this is the model we want to have in production. So we are going to update, of course, our variable here that says this is going to be now n equal 3 to our trigrams. So that means the data set we're going to compute here will have changed. This data set will be sent. This data set will be passed to afterwards to the model. So our model is going to change, and since our model is going to change, our score eventually will be changing. So everything that we store here is going to be different. And what DDS does is that by keeping this under some annotation like this, it will track all the changes in your code and be able to know. It will be able to know when to recompute all the missing elements as you do code changes. So just like a picture is worth 1,000 words, I want to show you what it looks like in a demonstration. So I'm going to switch to a Databricks notebook. So this is running here on Databricks, and right now I have just a simple test cluster here. So and you can use any cluster that supports Python on Databricks. So I have already installed this library on this notebook, and this is just a matter of running pip install in order to do that. So because we're talking about storage, DDS just needs one piece of information about where you want to store elements. And here we're going to use DBFS, which is the Databricks file system for doing that. So I am just going to instruct DDS to do that. And let's see if the connection is going to be good for doing that. So it seems to have run. Yes. So let's say now, just as a simple hello world example, I have a function that computes an enormous amount of data, which is the small string here, hello world. And I would like to say that this function is a data function. I would like to keep its result to a certain path, and I would like to cache it and be able to reuse it later. So if I simply call this, so I can just run this function as it would usually, it is going to give me the results. So far, no big change. And as you can tell here, I'm also having a message to say that it executed. Okay, so far so good. There is nothing to expect, no changes to expect. One big difference to start with is that now, when I executed this function, the result is also stored in the Databricks file system in this path here, hello data, which corresponds to the path that I said here. I want this result to be stored there, and we can put any sort of path to make that happen. And remember the signatures I was talking about. Well, DDS is also going to track under the signature of this particular function also its result, so that it keeps also a copy of the results under the signature. And we'll see why this is so interesting afterwards. So now if I rerun this function, it is going, of course, to give me the result. But you notice there's no more message anymore about saying that it is executing the function. What happened here is that when I call this function, the DDS framework noticed that I had run it before, like recomputing a signature. It noticed that it had already stored the result here. And as such, there's no need to run the function anymore. The result has already been calculated. It can simply give me back the result. Now, if I decide, for example, to change this function, say I don't like it, I'm going to put a couple of exclamation marks like this. So now it is going to rerun it, and the signature of this function will be different. So if I check how many signatures it has, now there's a different one. Now it is going to give me the result for this signature here. So this way, DDS is tracking every execution that you do of your code and is able to match against previously executed code what you have done, and be able to give you directly the results if you need to. Now, if I remove my change, for example, I didn't like, after all, my exclamation marks, what is going to happen? Again, we don't see our message saying that it is executing. What happened here is that DDS noticed that this function corresponding to the signature was already computed here. So no need to recalculate it again. I can simply give some results. I can simply give the result back. And here it is simply giving me the result back without having to execute again this function. Okay, so that looks like so far a nice trick. How does it really help us in practice? So one thing that it can give us already is the ability to track all the dependencies between different functions, between different data functions. So let's say that you start to have a pipeline that is, okay, not very complicated, but it starts to be not completely trivial. And here I have a first function, f1, that I want to store. It's a data function. Then this function is going to be used as an input for these other functions, and so on until this big function f that contains everything. So DDS, because it tracks the code before it executes, can be used to also give us the list of all the dependencies between each of these data functions and each of the paths that we update. So just by looking at the code, just by introspecting it, and just because I put these annotations, I can look into the code and say that this final function, this final result from this function 3 will depend on these two results here. And this is done without executing the code. This is just done by looking at the content. So even before calculating anything, even if it is a machine learning model, even if it is a terabyte transform, I currently know the dependencies. So now just to make sure we have the results, let's execute it. And one thing I want to just point out before moving on is that one of these functions here depended on this variable. I'm saying that here, I really like this variable. I'm going to just add it as a dependency. So let's say now that I want to update this variable. Let's say that 3 was not a good value. Let's say it's a hyperparameter and I want to update it. So if we update this value, then DDS will see that some of the signatures will change because the dependencies of like such as outside variable will have changed. And thanks to that, it can already tell you, even before executing the function, that these two functions, same signature, same result, no need to execute it, the result can be reserved. But this one is going to be updated. And by dependencies, this one is also great. The final one, B3, is going to be also updated. And all this sort of calculation can be run without having to run the code, simply by introspecting the Python code that you have already written. So now if we look at the full data science pipeline, this is where things can start to be really interesting. So let's say that I want to run a standard wine quality dataset check, and I'm going to download the data from the internet to make sure that I do not have to download it every time I run it. Right now, it's taking a few seconds. But to make sure I do not want to run it all the time, I'm going to mark it as a data function. And here you can see again, I'm running it again. It has executed. The code has not changed. So it is simply going to give me the same result. No need to go to the internet to fetch it again. The code is the same. The results are going to be the same. Now I'm going to run your standard machine learning pipeline. And for that, I'm going to do the traditional approach of taking my data, splitting it into a trace and test score, building a model based on the training data and evaluating it against the test data. And here I want also to track the result of my model, just like I explained before. And I want also to store my statistics. So far, so good. I'm running my pipeline. I can see that it ran the model, it ran the statistics. Now, if I evaluate it again, as you can imagine, nothing is going to happen because DDS captured the fact and found out about the fact that no code has changed. So the result is the same, so no need to rerun it. I still have my results here with my statistics, all in JSON. I can read it somewhere else. Now, if I start to make some changes, for example, such as the statistics, let's say I want to change that. Let's say I want to add also some remaining square. So what do you think is going to happen? So far, I have not done any change on how I build my model. I have done changes on the function that computes the statistics. So if I run it, it is going to reuse the model that it built before because the code has not changed. It is going to recompute the statistics. This is why you see here, it is in the model statistics. And it is going to store them where I asked the DDS framework to store them, all on the Databricks file system, now with the update. And if I say, yeah, this is actually not the change I wanted to do, so I can just revert this change. Well, as we did before, there's nothing to rerun because it has run before, the code has been already seen before, and it is going to backtrack the changes here. So now I'm back to just having that. So this gives you an overview about how DDS can help you while running some data pipelines, which is that it can, by tracking the code that you have written, if you have already run a piece of code, DDS will detect that and will simply give you directly the result. And if you have only pieces of your code that needs updates, then if you have updated some portion of your code, DDS will be able to detect that you have only updated some portions and reuse already some other pieces. So here, it reused the model, it just updated the model statistics. And you can see how this already can very quickly accelerate the development of models or any sort of data set, in the sense that you don't really need to care about how they're being stored. You simply write your code, it produces data frame, it produces a model, you just put it there, and you just say, let's store it here. So based on that, so I want to go a little bit about how it works, and this will explain also some of the why some of the changes were made this way. So in order to compute the signatures corresponding to your code, it is actually in Python not too difficult to do. Because Python already has a lot of machinery to introspect your code, and this is why it is such a good language for being used as a glue for doing all sorts of data science and machine learning tools. So in this case, if we take this function here, and if we want to compute this, if we take our function that build a training data set based on some animals, well, we can take the hash of everything it depends on and compute it very quickly, actually. So if we take the hash of, here depend on the file name, so we add the file name. It depends on another function, so we recursively add this function. It depends on some pandas function. We can also build that and cache that, and so on. So we can, this is how in less than a millisecond, it can quickly build a signature of large bodies of codes if necessary. And of course, the syntax can be sometimes a bit unwieldy. So this is why for most usage, as I was showing you, you can simply write your codes with like you would normally. It would return an object, and you simply annotate it with this annotation to say that this is where you want to track where you want to get the results. And if your function takes no argument, this is all you have to do. And you get all the benefits of DDS for doing that. So you can think about it already just by using this decoration annotation, simply as a way to memorize and to cache results. But since it also tracks your code changes, it is actually much more powerful than that. So based on that, it really opens a lot of very intriguing possibilities, I believe. So here is one example that I briefly mentioned that based on the example about graphical representation. So since every artifact, every piece of data of interest is tracked by a path, and because we can compute all the dependencies between them even before any computation, this means that you can put significantly complex graph and pipelines inside the piece of code, and you can track all the dependencies that they have. So this is an example here of a data pipeline that is being run in production in one European bank using DDS. And before doing any sort of code change, we ask DDS to produce the graph of dependencies and to see what the changes are going to be. And this takes, generating this graph on a code base of about 50,000 lines of code of Python takes about 0.2 of a second. So it's really quick to do. And in this case, one of my colleagues decided to make a change in the code that builds a feature here. And we can immediately, as part of the review process and as part of the update process of dataset, even before changing any dataset, we can already infer what the changes will be on across all the data produced by the team. So this is already a powerful feature because some of the changes, for example, changing a value, might go actually much deeper and start to update large chunks. And then we know already in advance that it's going to be such a large change. So being able to visualize the complexity of a data pipeline is already very helpful. Another piece, which I think is something that is even more powerful in that sense, but that is actually quite easily with DDS, is how to deal with the problems of data evolutions when combined with the evolution of software using Git or any of these versioning systems, for example. So if we start from code that generate like our piece of code that generates data, and this code is written in the master branch of a source code repository. This is our code as before. And when we evaluate this code, as I was showing you on the demo, we're going to, let's say that we're going to compute two elements, like one model and some test scores. And each of them will have a specific signature that we already have in our data store. So it could be DBFS for Databricks users. It could be local or NFS or any of these other data stores. Now, someone is going to fork the code and is going to create a new branch. So this is just a code change. This is just a code branch, a code fork. When this person is going to run this code, this locally in their own view, they will see that when they train the model, there will be a model object associated to it, again, a test score associated to it, and the signatures have not changed. So the data has already been stored in a central location. No need to do any updates here. Now they're going to make some changes in their code. And let's say that we're going to change this value. So a lot of the values will have different, a lot of the variables here will have different values. And when they run it, because they did a change in their code, some updates will happen after that in the signatures of these functions, the signatures associated to these objects. So this will populate this will point to new objects, and this will populate some new elements. Now, when they go through the code review process and when they go through the merging processes of the code, their code will be integrated into the master branch. And in the meantime, these models could take hours to train, but it doesn't matter because, as we saw, once you run it once, if your code has not changed, your data will be stored in this one place. So now that the code has been run in the master branch, if someone checks out the master branch and runs it again, what will happen? Well, then when they run their code, the signatures will be such. They have already been seen. They have already been computed. So the data sets are going to be already pointing directly to objects that are already available. And this operation is very cheap. So this means that even if a branch can train models that can take hours to run, anybody depending on this code after it has merged will be able to run it and evaluate it and get the results of it in a matter of seconds. And that means that corresponds to the general philosophy of writing and creating artifacts is expensive. Reading them should be as fast as possible. So this is how I think it enabled really this is how amongst collaborators, it has enabled a very smooth flow for updating data set and making changes in data science code, because the owner of a branch and the person responsible for a branch can wait for large computation to finish, but when they have finished it, this data corresponding to this calculation has been stored, and then someone else who checks out the branch will immediately get the result without having to rerun them again, because the code will be the same, and so the output will be the same. So what is the status of this project of DDS? So it is available on PyPy and also on the public GitHub repository. You can use it. Everything that I showed in this notebook, this is a public notebook. You can try it out and it will run as expected. The documentation also on GitHub and on the documentation website includes other examples for Jupyter, for example, if you want to run it locally and try it locally. It is used right now in production within a large European bank. How stable is it? Right now, you should assume that it is in the beta version. And by this, I mean that the API for the user, so how you integrate with the code, is not expected to change. Some other function might be added, but the existing one should not be expected to change. However, the underlying algorithm that is used for computing signatures, the hashing algorithm, may change to increase for better performance reasons. So which means that if an update, through an update of DDS, The same code may retrigger calculations simply because it computes signatures differently, and they are the base for all the calculation afterwards. A couple of features are currently under consideration. One of them is having a direct access to objects without having to call their functions. And the other is, I think, quite interesting for the user, because as you saw with this with the diagram that I was showing, as you saw in these diagrams, this gives the dependencies between all the elements. And once, assuming there is no other dependency, which is typically a fair assumption for these data objects, assuming there's no other dependencies, then this gives an implicit way of automatically executing all these operations in parallel. This will give a way to recompute everything from scratch if necessary, in parallel and without any other user input. So I think this is another powerful feature that has been requested by users. So some features of Python are currently not supported. And actually, what are some of the limitations around that right now? So all the basic features are supported, but Python is a very rich language. So a couple of things still need some tuning. One of them is adding keyworded arguments, adding some other support for some of the more advanced ways of using classes, and also more built-in support for complex objects like Dask data frames and, for example, PyTorch models. So this is planned for within the next few months. Some other aspects of Python are currently not under consideration simply because their complexity and usage in terms of the complexity does not really translate into really strong benefits for the data science community for Python features. And here I'm thinking about more advanced things such as futures, asynchronous functions, continuation, and so on. So these might be added, but they might require a bit of rethinking of some aspect. And of course, this is an open source project. So if you have a brilliant idea, please, your contributions are more than welcome. So here I described something which is a software package that helps you drive, I believe, the data science in a way that is more natural and easier for users to deal with. And when you reflect a bit on what it does, and what are the underlying assumptions, it really looks at data science as if it had two components. One is raw data, so data that you get and you're not assumed to be transformed, and software code. So everything that you write to produce a new derived piece of data. And it could be machine learning models, data sets, statistics, images, anything. And the code that you write for doing that tends to be very, very specific and from the perspective of computer engineering. In particular, it is very good for caching because we always want to store our results from a data science pipeline. And it is also very good for giving it back without knowing where it has been before. And for typically also being deterministic. So in practice, it tends to be, in technical terms, that means it tends to be very, very good for referential transparency. So this is why when we think about what we do in data science, I like to think that we can turn, thanks to frameworks like this, we can turn every sort of data integration problem, data evolution problem into something that we are more used to, which is a code management problem. Simply by being able to fork, come back, branch, merge, this is quite easy to approach using the tools of computer science, of the regular tools that we're used to, by building some bridges like DDS. So to conclude, I think there was a talk from Alexei Kaparty a couple of years ago about where he was lamenting on the fact that the tool chain for software 2.0, the integration of machine learning, data, and code does not exist yet. And I believe that one of the first steps that we can do is really seeing how we can seamlessly integrate the programming with data with the regular programming that we're used to. So I think this talk shows one possible approach, which is to break down the problem into raw data and code transform on top of that, and in which every data problem becomes essentially a coding problem. So thank you for your time, and I am looking forward for the questions.
Well, thank you, Tim. That was a really insightful and thought-provoking talk. A lot of questions actually have come up both in the LinkedIn channel as well as the YouTube. So let me start with some easy questions and then progress towards the more hard ones. Somebody pointed out, when you actually have variables or arguments or parameters in your function that you actually have decorated with EDS, and it maintains internal state in that function, what happens then?
Yes, this is actually, I'm very glad that this person saw it, and this is actually when I think crucial aspect where it can help. If we take this example here, this function build model here takes complex arguments. These arguments come from complex transforms, and they can evolve. And the assumption being done here is that the argument is too complex to deal with precisely. So how about we look at the code that produces it? We know that any argument that will be here, simply because of how computer software is written, any argument that is here will come either from the function or from somewhere outside. And anything can happen here, but as long as we track the code that was being used to produce it, that's all we need to do. So this is how DDS can actually bypass this problem of highly complex arguments by simply tracking the code that is used to generating them instead of tracking themselves. There is actually more example in the documentation about how it works in practice.
Now, I mean, while you're on that particular piece of code, I actually see the definition pipeline. What if I wanted to use MLflow to track the data here? Would that actually change the way it works? I mean, does it seamlessly integrate with MLflow? Does it complement it? So I could actually track all my metrics over here and put all my data and everything using MLflow in here. Would I be able to do that?
Exactly, yes. And this is definitely, so the DDS is designed to cooperate with MLflow. MLflow is excellent for solving a lot of problems which are complementary to DDS, namely exploring the set of variables, exploring the different hyperparameters for doing tuning and finding the proper way of doing it, and making this model available in other pieces of your pipeline. DDS is helping you with the reproducibility of it and making sure that if you need to collaborate for some of these experiments with other people, then you can do that in a seamless fashion. So when do you need to collaborate with people? Typically, it is when you have settled on a particular examples, and nothing prevents you from using MLflow to create an experiment, saying this is the run ID that you want to use for the model, and then putting it as an argument. That's one way. Or, as actually it is being used in one of the pipelines we have, MLflow is used by data scientists in an exploratory fashion to find the right set of hyperparameters. Then the model is retuned, and then essentially there's only the one and true model being stored. And once and this model is being tracked with DDS, but then it is again published with the MLflow.
Yeah, I mean, I saw some parallels in terms of how you're actually doing the schemas for each and every function where you're actually storing the schema. You're taking the hash of that and then keeping that. And if the function signature changes or any code changes, you actually effectively change the entire way you're actually creating the pipeline, which somehow, to some extent, is similar to if you change your input data to MLflow, then we actually keep track of the schemas. And then if you're trying to infer something that is not compatible with the schema, we let you know. So that was actually a good complementary piece there. Another question that I have that came from Thunder Snow on YouTube. You said, are you able to fix a data dependency version for tree of calculations? Are you able to fix a data dependency version for a tree of calculations? I'm not quite sure what he means by that, but
so how interpret the question, I guess, and the answer is the affirmative, is that here If you look at the calculation, all these functions here refer to each other. And it's more than a tree, actually. It's a complete directed graph taking all the calculations. And DDS is able to infer all the dependencies and also how they actually relate to each other and how they can be shared with each other. When you do one call to produce this data table, it will be able to infer that this data table could be used across multiple elements. So I think beyond the tree, you can pass arbitrary acyclic graph, and actually it will prevent you from trying to make a cycle, which is a good thing. And I think in that sense also it helps you sanitize your data pipelines.
And I think the follow-up question by the same person is, could two organizations share edges on the data dependency graph?
Yes, and when you look, actually, this is how actually Databricks, solutions like Databricks with something like DDS works very well together, because as I was mentioning with this example here, we assume this works, this kind of merging, branching, collaboration works when you have a single store that all the users can use when they compute their signatures, where they simply store all their artifacts. They might have different views about what is the model, what are the test scores depending on their versions, but they share essentially an underlying true representation of any function that was executed to any signature. It is stored in one place. And this is how in an environment like Databricks, for example, we collaborate where someone using a notebook, one data scientist uses a notebook to create and populate the data store, and then another data scientist uses the essentially pre-calculated results to rely on that. And this enables really seamless collaboration between the two.
A different question on the Q&A on Zoom is that how much data can be cached, and is the cache persistent or in memory? And if it's persistent, do you have a choice of where you can actually cache the data? Does it always have to be DBFS?
Yes.
Or if you're not using Databricks, can you actually put the cache on S3 bucket or any other external storage?
So I am trying to recover my mouse, and actually I can show you an example of how the cache is persistent. So this notebook, and here I'm using the Databricks environment, which means that in this case, I'm using the Databricks file system, which is permanent.
Right.
Now let's say I'm going to detach and reattach my notebook. Okay, now it's telling me horrible things about clearing up my environment, etc., etc. Now, if I rerun this notebook, let's see how it goes. If I rerun this notebook, then once I run it, it is not going to re-execute any of the calculation in this notebook because the code has not changed. The cache is still persisted on the Databricks file system. So there's no need to recompute anything. Actually, as a matter of fact, running a notebook that processes terabytes of data in hours will simply run in the 10th of a second once it has done this. And nowadays, I have to say that within our group, the expectation is that running any notebook should take less than 2 seconds. If it takes more, then we simply cache things and we make sure that then it doesn't need to run. You can do that also for displays. You can do that for any artifact that you produce. Jules, I believe you're on mute for quite a while.
Yes, I did. So I'm going to ask a final question. I think we only have 1 minute left, and this is again from Thunder Snow, who's asking: are data versions tracked in Delta's transaction log? I doubt, because we're not using Delta here, but you can probably clarify that. The data dependency graph by frames. This is really great. He likes it, but he's just asking: are the versions that you actually create, are they being tracked in Delta Lake? Or if you wanted to track them in Delta Lake, you presumably can, because where you store is up to you, isn't it?
Exactly. So, for example, here I'm storing it on the Databricks file system, but it could be exactly on DBFS. It could be behind the scene. It could be a Delta store. There is no limitation to that. So you can always backtrack, come back. And this is actually complementary, because DDS tells you what should be updated. It doesn't tell you how it should be stored and how to deal, and it deals simply with the idea that it will overwrite everything that needs to be updated. If you are unhappy with your transform, this is where Delta Lake can help you. You can say, nope, that's not what I wanted to do. I'm going to take I'm going to roll back to another version.
Okay, lovely. Well, that answers almost all the questions we actually have for the allocated time we have. We want to thank you, Tim, for sharing this great software that propels people to thinking about in the new way of Software 2.0. And I want to thank Karen for hosting and organizing this last meetup. And we wish you all a happy holidays and a safe holidays.